Central Protocol Diana landing. Distance covered 67
Okay, everyone can settle down and we're ready to start. Thank you very much for your patience. We had some technical difficulties, but we managed to salvage some of the very cool videos that you've been using. But I think even cooler is your speaker tonight. We're very fortunate to have Dr. Claudia Alexander. She's from NASA. She's the lead project scientist for the Rosetta Mission. You guys heard of the Rosetta Mission?
Yes.
Okay, that's why you're here, right?
Yes.
How did you get into a Comet? Well, she's at the NASA Jet Propulsion Laboratory, and I'm not going to say too much about her because she said she must get on with the presentation, and we'll have time for questions at the end. Let's give her a warm up.
Rosetta, and let's hit this movie and let's have the lights go down, please. There's my signal there.
Rosetta spacecraft set off for a London landing at the distant Comet 67P to New Jersey.
Comets are really important. They're like a time capsule back to our past. They were formed just as the planets were formed in the solar system formation.
You'd like to understand, is that the original material that the solar system kind of went from something like that to water and oceans and palm trees and the like? How do we know what our original solar system was made out of? Does the comet really represent some of that original material? And it's so very different. How do we get here from there to where we are now?
Okay, well, it looks like we still may be having a few technical difficulties. Hopefully we will we'll be able to smooth that out. I want to point out this is a European Space Agency mission. We have talked about branding, agency branding, and the overwhelmingness of the NASA brand, and that the European Space Agency is really, with Rosetta, trying to establish itself as another national agency that does a great job with interplanetary missions. And what I'm going to say today, someone suggested that I really should talk about this mission as the mission that was slated for disaster, a mission that was never going to make it from the start. Okay, my European colleagues would be very irritated to know that that's how I was pitching it, but it kind of works. Okay. We started out in a minute, or maybe with the next slide, I'll show you. Let me see if I can find these guys. Back in the 80s, I've been talking to young people at the conference today who were born maybe 15 years ago, and the 80s is like incredibly ancient history. We're not even born, and are you kidding? I'm going to be 30 years old before I get to actually explore a comet. The people that you see in this picture laid the groundwork, and that's how long it takes to get a mission like Rosetta off the ground. A flagship style, what we would call at NASA, a flagship style, or at ESA what they call their cornerstone missions. So this is the biggest mission, the most expensive mission that you can put together, and you can see that they were putting it together for what they call the Horizon 2000, which is this is where we think we're going to be in the year 2000, and this is what we would like to be exploring. So even back then, Rosetta was having trouble getting off the ground because it's ambitious. What we want is some of the original material of the solar system. We want to take a laboratory to a comet and dig around in there and find out what that stuff is made of. But it turns out the European Space Agency couldn't pull that off with what they had. They really needed to partner with NASA. And in those days, NASA was interested in partnering with other people. NASA's still interested in partnering with other agencies, but we've gone through some wrinkles where they started saying, well, you're sharing technology with other countries, and you can't do that. So that was not NASA, that was another agency in the government. And we had to say, what are you talking about? Science is collaborative, so, get out of our way, is what we tried to say, but then they said we had to invent some rules. But along the way, Rosetta, the rocket that we were going to launch on, blew up. So this was about 90 days before our launch, and we said, oh. And the French space agency says, do not worry, we will launch you. We have no problems. But the very next launch also had a problem, and then a test launch had to be destroyed. And so we said, you guys fix the rocket, and we will wait. So we had to take a launch delay, and that meant that instead of finishing in 2011, which was our original arrival date and mission, we were extended by 3 years, and we had to go way out, much deeper into the solar system than was originally planned. Our target changed from a small, teeny-weeny Comet Bertanen, to a ginormous comet with a really unwieldy name called Churyumov-Gerasimenko. And the lander guys said, you are got to be kidding. We designed the lander with the shock absorbers and the landing gear for a small, low-gravity target, not a large, more bigger gravity target. So we already started out with some aspects of risk. I'll call it risk. The guy who was coaching me said, it was failure. But no, we knew that, okay, this is now going to be riskier than we originally planned. And one of the wrinkles is that when you go this far out, you don't have the power to stay, to keep all the instruments warm. So one of the other aspects that had us slated for failure has to do with the fact that we had to turn the spacecraft off for almost 3 years. And I'll be honest, my bosses at JPL, which is an arm, a center of NASA, had a fit. They said, you tell those people they cannot turn the spacecraft off. You never turn the spacecraft off. And, as if the Europeans didn't know that, right? As if the Europeans were just like, well, let's just turn the spacecraft off. And so, believe it or not, one of my jobs was to coach the Europeans, because I was under orders to conduct a review. We're going to conduct a review of this mission, and we are going to straighten this out. Okay. NASA cannot conduct a review of a European. So my job was to say, we won't call it a review, we'll call it a technical interchange meeting, and we will politely ask if they would be kind enough to come to JPL to discuss the turning off of the spacecraft with some of our really smart civil engineers and systems guys. Because of our instruments, we were worried about our guys. We don't really care about the rest of the spacecraft, just our NASA instruments, and whether they'll be able to have all the power they need to do our stuff. And they actually were gracious enough to come over, gritting their teeth, And it was a very productive meeting, and they accepted some recommendations that that hopefully did make it a more robust entry and exit from hibernation. We were particularly worried about coming out of hibernation. If you spin the spacecraft up, and then if for any reason it takes on a wobble while that's happening, it can start really wobbling, and then you're in trouble. Then you've got to figure out where it is, and it doesn't know where it is. And so we had one of our moments of escape from failure was in January, just about a year ago, when we woke up from hibernation and Rosetta phoned home. How many of you were around for that? How many of you saw that on TV? Rosetta phones home. Okay, so my mother was like, what does that mean? I didn't know how to explain it. So just for background, this is a comet. We have typically got one ginormous tail that's very beautiful. We also, if you're clever in observing, you'll see that there's another tail called the ion tail that is more directly the opposite direction of the magnetic field draping of the sun. The nucleus is in the middle of all that gas and dust. We wanted to get to the comet before it became this big structure in space. And we wanted to get there while it was quiescent in Lambda Manor. Here's another view of a comet. This is Comet Ison, another just gorgeous comet. And in the upper left, a really cool Chinese tapestry from maybe 1,000 years ago. A clever observer, night after night, seeing the changes in the comet. It takes maybe 60 to 90 days. Some people think the comet flies by in a flash, you know, at the speed of light or something. Or like a meteorite that is there in a blink of an eye and then is gone. No, a comet is usually in the sky for months. You can go out night after night and see it, like this clever Chinese guy did. In the case of Comet Ison, it was very, very bright at Jupiter. And people said, this comet is going to be, its tail is going to stretch from horizon to horizon. It's going to be bright as the full moon. And it fizzled, okay, so that was when it was at Jupiter, but by the time it got to around the Earth, it was almost not visible, and it crashed into the sun literally in a puff of vapor, and so much for Comet Ison, okay? So what are comets made of? This is one of the things we wanted to find out. I had my illustrator draw this, and I told her I wanted an intimate mixture of ice and dust. And she drew something which is kind of salt and pepper, which is really not as intimate as probably it is. So the dusty part, I tend to think of dust as like the dust under my bedroom. In my bedroom under the bed, the dust bunnies, which are more fibers than dust. So this is interplanetary dust, which is kind of the refractory part. It could be carbon, it could be silicon, it could be titanium. We're really anxious to get a chance to know what is that content of that refractory stuff. But the icy stuff we can see from the ground pretty much, but just the simple ice, it's water, carbon dioxide, carbon monoxide. We think there's many, many more, and we think there's got to be organics, at least on paper, there's organics, but we've never observed it. So one of the things we want to do, get to this comet and really dig into it and see, prove to ourselves that what we think should be there really is there. I also wanted to point out that the comet is very black. And when I said this earlier this morning, people were laughing. And yes, I said black, okay? Black as the toner that we used to use 10 or 15 years ago to print the black letters on documents. Okay, you remember that stuff? It was very, very dark. And that's how dark the comet is. And I don't know any ice that I can put together in my freezer that makes anything that is as dark as that. So this is a really extraterrestrial type of ice. And that's another thing we want to figure out is, you know, what is this stuff that comets are made? So one of the things that makes our mission unique is that we have very, very state-of-the-art sensitive, what we call mass spectrometers, or these are the things that can tell what the elements of the periodic table, they can actually tell what those elements are. And the best example of this is if a mass spectrometer has an aperture like this, and if I put something in my mouth, like an M&M's and a Reese's Pieces, I can tell the difference. And a mass spectrometer with these cometary particles is going to help tell the difference between some of these masses that are almost the same. And in this case, this is everything in or near mass 28. And in the old days, 10 years ago, I worked on Galileo, I worked on Cassini. The mass spectrometers could not tell the difference between any of these particles. And so we have a mass spectrometer that can sort this out, and in particular, we need to know what is the story with nitrogen. So I'm not going to tell you the nitrogen thing today. We're going to move on. We'll save that for another time. I'm also not going to talk much about our trying to understand how this comet works as a machine. But basically, the various materials out of which the comet is made are going to respond to the sunlight differently. And that'll tell us how sunlight goes in and gas is released. And that'll tell us a little bit more about how this comet is structured. We need to know, is it like a block of granite, or is it like a snowflake, where the particles only touch at certain indices, and that limits how they, or dictates how they conduct energy. So that's one of the things that we both want to know to know how it conducts energy, and then knowing that will tell us a little bit about how it responds as a machine. One of my favorite experiments, failure. Okay, the guy told me, you should emphasize the failure. So here's one that failed. It didn't fail, not yet. But I think that the guys are having an awfully hard time sorting this out. So this is cool because it's like an ultrasound of the nucleus, and you put a radio transponder on the surface, and you put one on the orbiter itself, and it sends the radio signals through, and you can take this ultrasound. It's called tomography. That's the type of experiment that it is. And you can see on the left is this radio waves pass through, and you've got these little nodules that could bounce things off. And on the right, maybe there's layers, and we can tell if there's layers inside. So we were looking for that. And I think the problem is that there's so many, the shape that we actually have is so complicated that they get bounces off of everything. And they can't tell what's just the edge of the comet and what's actually stuff that's inside. So this was one of my favorite experiments, and I'm really hoping that those guys can get it sorted out. So here's one of the movies that didn't play, which is a good thing because we want to move on. There's a beautiful galaxy in this picture, which I love because a galaxy is so far away outside of our galaxy itself. But the comet is in the red dot, and one of the very first things that happened when we arrived, and we were still getting set up, setting our campsite up, getting the tent erected, getting the campfire wood positioned for the campsite and everything, and the comet had an outburst. And I think that took me by surprise. I knew the comet could be active at that point, but not to have this big outburst and then go back down to normal. So that's still an unexplained phenomena, but I did this lecture at Fermilab last month, and they said, well, maybe you're doing something. And I thought, oh, because we were out near the asteroid belt, which is kind of filled with space, but it's not beyond the realm of possibility that we hit something small that shook it up. So it's great to talk to other scientists, actually. That's what that proves. So here's the reason why I love this movie is because it's so cute. We thought our comet was kind of round and it was going to have maybe some dimples on it. But this is a model we put together to show what we were going to do and fly around and do the mapping. And then this is what it really looks like, okay? So talk about setup for failure. We were not expecting this, okay? This is a bimodal. It's got two lobes. We think it looks a little bit like a rubber duck. I think it looks a little bit like the blue from the Monopoly game. I think that's because of the silvery look of it, but the shoe part and the leg part. But anyway, so the question is this one object, or is it with a weird erosion pattern, or is it two objects that sort of crash together in a slowly in the origin dance that in which we began? Here's another view of it. A beautiful object in space. It's got what looks like to terrestrial eyes a landslide. We've got this bite out in the middle. and you've got these dusty regions, and you've got what look like boulders. Also notice in the bottom area these roundish things, which are really getting our attention right now as after the first blush of looking at the object has passed. Here's an idea of the thermal history. We were very interested in figuring out if there are any weird thermal regions, temperature anomalies, because for the landing we wanted to avoid those. And what's interesting here is that the comet is right now in summer, northern hemisphere summer. And that neck area that I showed you is very quickly going to go completely into the dark and be dark for the rest of the swing around the sun. So the part that's the most active right now is probably very soon going to turn into the part that's coldest, and maybe a cold trap. And this thermal, and then the southern hemisphere will be in the sun, in the summer, very short, different object very soon. I think the main part I wanted to say in this slide is that the thermal temperature at the surface is warmer than usual, but not inconsistent with a very dusty object that's very insulating. Here's an idea roughly of the size scale of it. It's about 4 kilometers in one direction and about 2.3 kilometers in the other direction. I've had people send me pictures of it laying over the city of Los Angeles or laying over the city of Tokyo. Some of you may have seen these online. And people call me up and go, did you get that right? And yeah, it's about, fits into the size of metropolitan Los Angeles, and then in the vertical direction, it stretches up about 10 times the tallest building in the city. So that gives you an idea of the approximate size. It's big, but it's not that big. Here's another view of what looks clearly like jets coming out of that central neck area. But I think for me, the sensors are telling us that the whole surface is active, and I'm really curious about what it is that makes it look like jets to the eye, because there may not be that much difference between what you see here and what's going on all over the comet. And we are hoping to fly through one of these jets later in the summer. And my question for those guys is, how do you know you're in one when you fly through it? So we'll see. We'll see if they can tell. That's my secret. Wondering if they're really not that massive. This is again looking at the surface, and at first with eyes trained with terrestrial geology, you say, wow, there's boulders there scattered about, and it looks like a landslide there in the upper left, and you've got these dusty regions, plains, let's call them plains. And we've got sand dunes going on. But, for an airless body, how do you get boulders? Okay, how do you get sand dunes? What is the process that leads to that? So I think the boulders are now getting our attention because possibly what I'm not going to show in this particular presentation is what they call goosebump terrain, or the dragon eggs. And they are seeing these. And you can imagine if something laid down at the dawn of the solar system, making these globules of round stuff becoming coagulated together. And so it's possible, or at least we're asking ourselves, are those so-called boulders maybe an example of the way in which the material was laid down to make this body what it is? So how do you land on a comet and not fail? So you don't want to run into the cliffs. That's definite failure, okay? You don't want to be blown away by gas coming out of a vent. That would definitely be failure. You want a nice flat place to set the lander down. That's what we're looking for when we're going to select a landing site. And here we go. Nice flat place. Anywhere there that you find one would be good. And then one of the reasons that makes Rosetta almost slated for failure is that we did not get the high-resolution pictures for the picking of the landing site until after the landing, so sample landing sites had to be picked. So what the Europeans did was very aggressive. I think people have asked me, NASA will never do anything. NASA doesn't take on any risk anymore. Why would NASA have done something like this? No. NASA NASA would never have done anything like this, and NASA didn't do this. NASA backed out of it, and one of the reasons is that you go first and you do your reconnaissance, you do your mapping, you figure out what are all the wrinkles and strange things about the body, you figure out its mass, you get its gravity, including the secondary and tertiary lobes of that. These are all things that we did not know when we entered orbit. We're still scrambling to get the shape, the mass, the gravity in order to enter orbit. I will show that in a few minutes. So what ESA did was do their reconnaissance and the landing in the same 90 days. And that's very aggressive, bold, and pretty gutsy. So I do have to hand it to them. That was awesome. So here is an example of our going into orbit, and it's an example of how tricky it is to orbit a body like this. So they tell me that dynamically speaking, when you have a small body with almost no gravity, then the positions of the sun and the other planets are almost as important in terms of pulling the spacecraft around as this low gravity object. So you can't really go into orbit until you get very close. So they designed what they call square orbits, which just blew my mind. What is a square orbit? What we have is a triangular orbit, and you see how the spacecraft pauses and changes direction, does a complete, it goes into a vertice and goes into the other direction. So it's kind of pause, change direction, and then, we would do this at what they call isocahedral shapes, which is a fancy word for a square orbit. The actual atmosphere, you can see in this cute little drawing with our still round model, that the atmosphere is still is active, even though we're getting ready for landing. Even though it's tenuous, that will drag on the solar panels. And it was tricky to navigate around there. And so tricky that the scientists wanted to go. We want to start collecting science, and the navigator said, we have to learn how to fly around this thing. Please, we need 6 weeks, 6 to 8 weeks. And JPL was so fascinated by this that they sent a couple of the best navigators that they had at JPL to shadow the European navigators and watch them learn how to navigate around this very tricky object. So for landing sites, I mentioned my favorite experiment, the concert. We wanted to be able to land where those radio waves could go through the body. So that meant certain places outlined in green here. We needed some places where the solar panels could get enough diurnal sunlight. So that left us with a certain number of places. And let me show this movie about how the lander deployment was supposed to go. European Space Agency, there's the brand. Okay, so basically what I want to show for here is we kick the lander off, get off the spacecraft. You hit the eject button, you're going. And then once it was free, the lander legs were supposed to deploy. The lander legs were supposed to deploy. And here at the very top, the little white canister was a retro rocket, which was supposed to hold us down. And then we had in the legs, which are supposed to deploy, we have screws to screw us in. And we have two harpoons that were supposed to attach us. See how easy that was? It's going to be so easy. 3 fail-safe mechanisms to make sure that the lander is affixed to the surface of the space. Of the comet. No problem. So here is, this is, once we got the high resolution images, this is a little movie of the landing site. It was never a good landing site. It was kind of the best of the worst places. But we were looking for a place that didn't have slopes that were bigger than 30 degrees. And that just really looks terrible, okay? Almost large cliffs in the vicinity and almost no flat area. So what we wanted to avoid was tumbling down. We wanted to avoid being blown away by some active area. We wanted to avoid hitting a cliff, okay? And what I was principally worried about, we wanted to avoid sinking down into this overlayer to the point where we would not be able to operate the instruments. And I was principally worried about that, seeing all of the planes of dust in the, some of those early pictures. So I remember making a bet with Jim Green, who's our manager at NASA headquarters, as to how deep we would sink. Here's another look at the landing sites that were picked. None of them looked very good, unfortunately, and again, because we were slated for failure, the landing ellipses were enormous. 400 meters landing ellipse, that's enormous. So it's almost like you don't know where you're going. You're just going to do this and just drop it, and you don't know where you're going. It turns out that the landing ellipse, when those guys practiced, the landing ellipse got really tight and was really good by the end. And you see that in the end. I'm going to skip this, and I'm going to, oh, here we go. So here is the picture of the orbiter from the lander as Philae was being ejected. So this is bye-bye mothership, and I'm on my way. And then here is the lander with the legs deployed, like they were supposed to in the movie. And we were supposed to get this picture a half an hour after the ejection, and we did not get this first picture for about 3.5 hours. So we were quite worried. Did the legs didn't deploy? It's not falling, and we were in the waiting room with a lot of nail biting going on. Here it is again a little bit later. Here it is again a little bit later. Here is a picture of the landing coming down onto the surface of the comet from the lander, and one of the landing legs is what you see in the upper right corner. Here we are on target. The red target is looking good in terms of relatively flat with no cliffs in the vicinity. This is the picture just before touchdown, and we narrowly missed this ginormous rock in the upper right there. But an interesting thing about the comet geology is that we think that comets are what we call friable. That means that it's like a log that's been in the fire burning, and it looks solid, but when you go to pick it up, it just crumbles in a puff of dust. Okay, so we think comets are held together really tenuously that way, and it's not clear that if we would have hit this piece of rock, if we can call it that, that it wouldn't be the rock that would crumble in a puff of dust. Fortunately, we didn't have to find that out because we didn't hit it. Here's another shot. Oh, no, I don't want to talk about this. I'm going to talk about this shot. Okay, so here we have a sequence, a time sequence of the landing. In the lower left, you can see Philae floating down. It covered 21 kilometers in 7 hours, so that gives you roughly an idea of how fast it was going, because you can do the math. So the upper two are the landing site before on the right and after touchdown on the left. And the interesting thing is, clearly there's 3 little touchdown holes, and you're tempted to think at first that those 3 are the legs going down. But in fact, the biggest one on the lowest one is about 4 meters in diameter. That's about the diameter of the extended legs of the lander. And it's about 1 meter deep. So what we think happened is that the lander went in, sank in, just as I bet Jim Green that it would, but the compressibility of the material, as it compressed, it got harder. And there are many examples of materials that do that on Earth. You press it down and it gets harder to the point where it bounced the lander out again. And then the hole continued to collapse down another half meter. So it's a really interesting example of something that's both hard and weak at the same time. It's just fascinating. Here is where we think the lander, the red part is where it landed, and then it may have hit the rim of this very large crater-like feature, and then fell into an area in the blue. We don't know where it is right now, but somewhere in that blue area. And I'm telling you, every week, one of the graduate students at the camera team comes forward and says, I found it. And so they have picture after picture of things that look like they might be the planet from all over the surface. This is, okay, so once we got established in the little ditch where we landed, the panoramic camera was able to do its job and take these incredible pictures. There's even a picture in the upper left corner called the perihelion cliff. And unfortunately, I can't show you that today, but I think the perihelion cliff picture and this little one that I'm going to show you in a minute are the most interesting. And it's an incredibly scientifically rich area to have landed and to be able to explore in terms of planetary science. So here's an incredibly interesting picture. The leg of the lander is down in front. We have two different kinds of terrain, it looks like to me. So you have a sort of rubble pile down at the left, down to very small size scales. It's a rubble pile, and it makes you wonder if this isn't the original material as it got laid down in this kind of globular, roundish, pebble-like configuration where it's not very hard. At the same time, to the right, you have what looks like a typical rock, or if this is an icy kind of material, like a block of ice. So is this how the material evolves as it goes around the sun? Does it harden as the thermal wave passes through it? So this is a great place to study that kind of physics, especially if we can study it at perihelion. So we had many experiments that ran. Every single experiment got a chance to run, and there was one that was supposed to test the hardness, and it tested every single setting and was not able to penetrate this material. So we really have a conundrum. It's very, very low density. We proved that it's a very low dense object, and yet there seem to be regions or pieces of it that are very hard. So it's a really, really fascinating type of material to study. We were there to start learning what that material is made of. So this is another picture from the lander. They are picking up these particles, and they have a lot of particles. And this is just one of the early ones, and it's made of sodium and magnesium and lots of other elements from the periodic table. And this is exciting to us because it validates what we think it ought to be made of. But I have to tell you that a lot of the PIs whine, no, I'm not going to get any particles. We have to be close. If we don't get close to the comet, I'm going to get nothing. Okay. Okay, so a lot of those guys have got so many particles they don't know what to do. And one experiment has a giant particle stuck in its aperture. So we have got a lot of riches right now to study. And for a project that was slated for failure, we are having an incredible gold mine of science and data coming back, and it's a lot of fun. So how much time do I have?
It's been as long as you like, as long as the audience.
All right. So what I'd like to talk about for maybe the next few minutes of the lecture is what we think Rosetta will tell us about the origins of the solar system, because that's one of the reasons that we're there. And so I'm going to play this movie, and hopefully it plays, and I'm going to speak over it. This is, it's called the Nice model, after the town of Nice, France. And this was the only thing that a bunch of astrophysicists could agree on back in 2006 on what happened in the dawn of the solar system. So we have an enormous molecular cloud, enormous. Millions of stars could be made out of the material that's in this cloud. And star formation could be going on in one part of the cloud, and other parts of the cloud might not know what's going on. But eventually part of it collapses down. We've got purple stuff and we've got yellow stuff. The purple stuff is what we call the Kuiper Belt, and the New Horizons project is headed there. We'll be there in June of this year. The yellow stuff is the comets that went out to the Oort cloud. Meanwhile, the giant planets are being formed, and the clumpy material that's making the giant planets is being gathered together, and they're getting more and more. But here's where we think that the orbits of these giant planets were not stable in the early days of the solar system. And so what ended up happening was that they got more and more unstable. My illustrator didn't really show that like I would have liked him to, because he only did it at the end, where we started having Uranus and Neptune started wobbling and oscillating back and forth in their orbits until they switched places. And when they switched places, it was a cataclysm that scattered all the rest of the debris in this part between Jupiter and Neptune. There it goes. There's the cataclysm. And voila, the solar system as we know it today, all clear, no comets, no debris, except for that purple stuff, which remains. So the idea is that Earth was forming at this time, and when the cataclysm happened, that it sent a lot of material into the inner solar system, and therefore that comets bring water to the Earth. So let me get there. Okay, so here's my, I think this is hilarious. It looks like Canada with the Hudson's Bay thing right there. And there's no way that this early in the solar system you'd have, North America. But the idea is that Earth is still forming, but it's getting hit massively in this late, massive bombardment of material that has water and ices included. And therefore, that material is what it is that rehydrates the Earth, that the Earth started out dry. And the thinking was that actually the material that did this for the Earth was from that purple stuff. Because there was one measurement done at Comet Hartley 2, where the flavor of water on Earth was isotopically the same as identical to the comet. So we were expecting with Rosetta that one of the first things we would confirm was that comets brought the water to the Earth. So I can reveal to you today, ladies and gentlemen, that Rosetta was a failure to confirm this, okay? Because the measurement came back, and the flavor of water on Comet Churyumov-Gerasimenko is nothing like either the flavor of Earth's water or the flavor of any other comet that we've ever measured. So it sends us back to the drawing board, which is a good thing. That's why we make the measurements. I'm a theoretician, I hate data. My advisor says to me one day, Claudia, don't get your hands dirty with data. Because there's nothing that ruins a good theory better than good data. And so here's another beautiful theory that's been ruined with some good data. But that means we have to do more thinking. The idea is that Earth formed, and it must have been dry because it's near the sun and the sun is hot. And icy stuff condenses further out, and you have to bring that icy stuff into the Earth in order to bring whatever water that Earth has in it. And I've never been a believer, so I constantly am arguing with my colleagues about this, but that's the idea, is that Earth, it has to have been dry, and so you're required to bring water from outside. And we just cannot prove that it was the comets. So here's the conclusion. That was one of our discoveries that we were looking for. It does show that Comet was probably formed in a very cold place, though. And that has an impact on our models and theories and so forth. We are continuing. We're waiting for the comet to really start putting forth this beautiful tail that we're expecting. We're expecting a bow shock to form, all of the plasma boundaries to start to take shape around the object. And we will be escorting the comet around perihelion, which is in August. And we hope to go all the way out until 2.5 AU, which is maybe we're looking at a 6 months extension. So we were going to be done at the end of 2015, but we think we'll be able to go, perhaps fingers crossed, another 6 months to continue. And as we go around, we will be looking at southern summer, so we'll be able to get a seasonal change. The southern half of the comet is expected to be completely different in its character than what we're seeing now, so it's going to completely change. And, okay, so everyone asked me, well, what's the future of the lander? Is it going to wake up? Are we going to get more measurements? Okay, we don't know where it is right now. We think that it will be able to wake up because it was getting about an hour of daylight per day, and that is enough to keep the batteries moving towards being fully charged. By the time we get closer to the sun, it will be getting 4 hours of sunlight per day, and that should be more than enough to get it charged up, and when it contacts us, we will be able to command it whether or not we know exactly where it is. So there's a really good chance that we'll be able to get the experiments going again, and wouldn't it be great when we're closer to perihelion to see a softer environment and be able to take a completely different set of measurements? That would be very exciting. We do hope to find exactly where it is, because my favorite experiment, the concert, the one with the ultrasound, they need to know exactly where it is in order to get some of the data cleaned up, to be able to say a little bit more about it. It's a good thing, okay? Instead of a failure, we have luck. We've had good luck all along. Being in the ditch where the lander is right now is not only incredibly scientifically interesting, but the perihelion cliff, the picture I couldn't show you, but there's an overhang that's shielding us from the sun, keeping us cool. We were originally supposed to basically burn up by about March. The electronics would warm up to the point where the lander would not be operable anymore. But now we're in a cooler place, protected from the sun, so we're going to be able to operate the lander through perihelion, and everyone is just thrilled. It's just awesome. So you can read more every single day about Rosetta on the blog. Our European colleagues try to put new stuff up every single day. And I thank you for your attention and interest in Rosetta.
Thank you very much, Claudia. That was really, really cool. And even though some of the videos didn't work, I think you guys will agree with me. It's so exciting just to watch her talk. It's better than any video. Okay, let's maybe have the lights up, and then we can open up for questions. Okay, you see I can go here. You can just.
Thanks. Very interesting. Would it be a fair observation to say that the whole Rosetta mission has left us with more questions than answers?
Yes, not only do I think that's a fair assessment, but I think that's what you want out of any space mission. Certainly when Galileo was done, we had more questions than answers, and inspired a whole new mission. With Cassini, we have a whole raft of new questions about Titan, for example, and we're really hoping to get another mission to go explore more about the potential for life in that environment. And you know, that's the advancement of our knowledge, is that the old questions become old with the improvement of our knowledge that opens your mind in new directions, and you start having more improved questions. That's part of the purpose of writing.
Other questions? Yeah. Anyone else put your hands up now so I can see you?
You mentioned that water will come out of the earth from a perfect cloud. But what happens on the other side?
Okay, so that the purple stuff would have rained down on all of the planets, and so you see the cratering, you know, on Mercury, Venus. Interesting, not as many craters, about the same crater rate as Earth. That means Venus is active and is turnover of the surface, just like Earth. Mars has definite evidence of cometary depositing of water, and Martian water is much closer to the flavor of cometary water than Earth water is. So, to me, that means that comets have are more important for depositing water on Mars than they are at Earth. Earth, so I think, okay, that Earth is able to bring out its own water. Maybe comets have brought some water to Earth, but maybe 10%. And in other respects, Earth has got its own mechanisms for bringing out water. But definitely those comets have had an impact on all of the inner solar system bodies.
Okay, let's see some more hands. I've got one question there.
Thank you, Claudia, for this beautiful presentation. It's wonderful. Thank you very much. Too much. I just want to know, why was this project given the name Rosetta? Two, do you think the purpose of this mission was achieved? And what advantage does North America?
So why the name Rosetta? Because just as the Rosetta Stone provided the keys of ancient language to the explorers of language, so will Rosetta provide the keys to the ancient solar system. Okay, so that's the basic idea. And yes, I think even now the objectives of Rosetta have been achieved. Okay, to obtain bits of the original solar material, to analyze them for what they will tell us about the dawn of the solar system. Even now, we have made incredible measurements, which I can't even tell you, okay, because they have to be published. Okay, so on the one hand, the peer review process makes sure that the measurements are accurate and have been reduced and analyzed properly. And I don't want to give away something because then if you go to the newspapers and give it away, that they won't be able to publish it as news. So some of the results we can't talk about yet, but some of them are puzzling. There's one molecule in particular that's been measured that has everybody scratching their heads, looking at interstellar clouds and trying to figure out how did we get that one inside of a comet. There are organics that are being measured, and that is confirmation that what we think about comets and how the cosmic rays and the ultraviolet light and all the things that bombard these ancient objects ends up resulting in complicated carbon molecules. So that helps us to confirm, whereas the result I just told you didn't confirm something we thought, where in other regards we're getting confirmation. And that helps us in terms of understanding, you know, why is Earth unique? What is it, what would we look for in other planets to try to find one that's like Earth? It's been like a gold mine. It's an amazing mission. And the third question was, yeah, well, for some people, it's enough. I've been studying the solar system and the collapse and the star forming process, and all of those questions for me are existential, right? How do stars form and how do they pass matter from one star to the next? So you have this gradual enrichment of the periodic table with every star. And I just am fascinated by that process from the Big Bang to what happens on Earth, and do you get even more of the periodic table? So for some people, those kind of questions will always be here. I mean, you can even be, I have talked to a homeless man in the park down the street from where I work. This guy is really amazing. He's drunk almost all the time. but he says, when we lost the spacecraft on Mars, he says, "Oh, didn't get your unit straight." And to me, everybody has, no matter what their walk of life is, they have these interests. They're interested in how did we get here, some of these existential questions. And then it turns out that for Rosetta, some people, like there's an instrument contribution from Poland, and that country has never contributed any instruments to space before. They are so proud to have been part of Rosetta to make this one instrument contribution, and they, you know, spent all their ingenuity on it. They built it for like $20,000, which is amazingly cheap, okay, for a space instrument. But that's the kind of benefit. Now you're giving opportunities for very small countries to collectively be part of something really important for space. It's something that people work very hard on and apply their ingenuity to, and they, it's an inspiring technology for, you know, other people doing things in Poland. So that, I think that's just one example.
Okay.
there was a question there and then.
Okay.
Yeah, I was just wondering, you said that the Comet, the water didn't match, the flavor was different from in the world. Could it be, I mean, does every Comet have the same basic flavor, or do Comets all have different flavors? So it could be that different Comets brought forward to it.
Okay. So, the Oort cloud comets, the yellow stuff in that movie, they all have, within certain error bars, but there's clearly a sort of a flat line family of flavor. That's closer to the Mars family. Mars kind of is up in that general direction. The one that we measured from the Kuiper belt, the purple stuff, the one measurement was exactly like Earth, and our comet is way above any of the other ones. So it's a surprise that it wasn't like the Oort cloud, the yellow stuff. That's a surprise. And so that sends us back to the drawing board. Was our solar nebula much more mixed? So we tend to think of this condensation line kind of like a snow line. Like you go up in altitude and snow begins to condense. You go out in the solar system and water starts to condense somewhere around the orbit of Ceres. But now you start to ask yourself, well, is it that clear cut? Do you have a gradient that's really clear, or was it a very, very mixed up place, really solar system? And it's a very chaotic place, a lot of collisions. So what's fascinating to me to think about is if life was forming on Earth about the same time, the very earliest amoebas, they weren't amoeba, that was more sophisticated, that was about a million years later, billion years later. But this chaotic environment where collisions are constantly happening, bringing new feeding material in constantly, you've got stuff hitting the Earth. You know, when you think about disasters that life has gone through, we have climate change. Well, that's kind of a disaster. But there have been other incredible disasters that life has managed to survive. So this measurement is maybe giving us a hint about how dynamic and chaotic it may have been in those early days. And I think that's fascinating to think about.
Again, we'll take two more quick questions, and I'll give priority to one of the learners here if you do. So you've got one question there. You might have another one. Unless any of the learners have questions.
Thank you very much, Doctor, for that talk. Just a possibility, as the comet with the unpronounced name gets closer to the sun, and even though Philae is sheltered at the moment, is there not a danger the comet will heat up to such an extent that it will damage some of the instruments in the solar planets? I mean, is this not a possibility? Why not? It's going to get hot, isn't it?
Yeah. Okay, so how hot do you think is hot?
Hot enough.
Okay, so I'll say room temperature. Okay, room temperature is not hot enough to, you know, melt fluid. But that's still pretty hot for the comet as we get closer to the sun. Remember, we're going to be outside the orbit of the Earth. The closest it comes to the sun is 1.2 AU. So that's outside the orbit of the Earth. So the average temperature is going to be that much colder. And then there's no greenhouse effect. So it's going to be like the moon.
I thought it was going to get closer to the sun.
Huh?
I thought it was going to get closer to the sun.
Yeah.
One last question now. No one's using the opportunity there, guys.
I think something that's really grabbed the popular imagination is this one-way ticket to Mars. That people are actually going to go, and a South African might be in that first batch of people. As a scientist, can I have your thoughts on that?
Okay. I think that it is incredibly unethical for a commercial company to propose to people that it's a one-way trip to Mars. I am appalled. And I wish that somebody would stand up and say, that is ridiculous. Okay, now maybe it's because I come out of a tradition where the charter was and to return them safely to the Earth. Okay, that's what the charter was for going to the moon. That the second half of that was so difficult for NASA to achieve, but they took it on as the most important part of the charter. It wasn't just get there and then say you achieved something. The achievement is to and return them safely to the Earth. Okay, that is the hardest part. And if you can't do that, you can't call yourself going to Mars. Okay, that's my opinion. Okay, and I realize that people want to feel like they're contributing to space exploration, and they want to be proud, and they're willing to, give their lives. But I think it doesn't have to be that way, and I just think that's it's unethical in my view.
We're gonna have to shut down now. I think let's give Claudia one more round. Claudia, you're an amazing speaker, and we are from Scifest. Thank you very much for coming. Thank you very much. Thanks for your patience. We pulled up our full hour slot, and I hope to see you again at tomorrow's session.